This talk's title maybe falls a little bit outside of the range of the other talks of today. And that's because mostly I've been a user of ML platforms, even though I've been involved in building or improving upon some of them. And so I'm going to talk about that through that lens, which I hope will be interesting to sort of like spark conversation and discussion about gaps that are still to be filled in many common platforms today. You know, obviously the question that I'm sure you all have great answers to is what is an ML platform? Lifting the description from Data Council's website. You know, the ML platform is about moving systems from development to deployment, and the tooling that makes this an organic process. I highlighted organic here because I think it's really interesting to think about the quality of data platforms based on how organic of a process they make model development and release to be. You can really see that it's like similar to engagement metrics for other products. A lot of what a data platform does is just reduce friction at various points of model training, model backtesting, etc. And so I thought, sort of based on my experience previously leading ML projects and being on a team that have used ML platforms, it'd be interesting to have a humble user review of ML platforms and some highlights of you know, feature gaps that might still be interesting. So what I want to cover is a little bit more about the surface area of ML platforms. I think, you know, in the talks today, you saw that there's really a wide range of what you can consider to be part of an ML platform, for sort of like model orchestration with things like Angelo, tools to prevent time traveling and data leakage, and online feature stores, which I believe Zipline helps with, and sort of also just general orchestration of all these workflows and putting them all together in a coherent whole. Then I'll highlight sort of 5 areas: offline data management, mostly, you know, within the lens of training models as opposed to just data management, validating model performance, deploying models, what happens after you deploy models, which sort of like both encompasses monitoring and alerting and preempting errors. So going back to ML platforms, this is you know, a sketch I made of what are all the areas that I think are covered by ML platforms. You can see that there's anything from continuous integration to purely application logic, especially around sort of like output validation and sort of feeding the right data set to a model, but also monitoring model inputs, model outputs, monitoring latency, etc. There's various such graphs online. This is from the great paper, Hidden Technical Depth in Machine Learning Systems. Would recommend this paper. It's by Google. If you haven't read it, it's really solid. And this is their sort of graph of what is an ML platform. What I find interesting is that they highlight that the machine learning code, right, is this very small subset in the middle here. And that you have all these giant systems that actually are doing most of the heavy lifting, as some of you are well aware of, I'm sure. I think one takeaway from this is that most machine learning products aren't about the ML at all. And in fact, most of the surface area of an ML application is not the model. That means 2 things that I think are important to realize. One is actually most of the problems will emerge outside of the model. You know, when things go horribly wrong at inference time, it's often not the case that the model is wrong in some way. It's the case that some assumption along the sort of data flow is broken, and that leads to a model breaking, or that leads to some results being displayed in an odd manner. The other observation is that means it's easier to fix the overarching system, the platform itself, than the model. In fact, you know, when you have had sort of like incidents and productions where, you know, like some model is performing poorly, if you've ever been involved with that, you'll know that like very rarely the solution is to retrain the model and redeploy it. One, because that's costly, and takes a lot of time, especially when you want to respond to an incident quickly. But two, because usually for most sort of battle tested models, you have many ways to recover from a model failing, and I'll talk about some of those ways later. So starting with offline data management, I think one sort of interesting use case of ML platforms is how they facilitate the relationship between models and data. So, if you think about the graph I drew at the start, well, this is mostly related to how do you backtest models and evaluate them. ML models don't exist without data sets, so making data gathering, iteration on data sets, feature generation, and model evaluation easy is sort of part of the contract of a platform that supports ML. As again, many of you, I'm sure, know, a model is sort of tied to its data set. The bottom right, I have an example of a simple model, but that is represents a phenomenon that basically exists everywhere, which is that if you train a model in this example on trying to forecast the volume of rain, and you train it on data from San Francisco, if you do inference in Seattle, that model will do really poorly. And so each model should be tied to a data set. Usually this is something that data scientists do themselves. They write in their Jupyter notebook that this is like the result of data from this range, from this query that maybe they've copy pasted, and that it was that feature version. A lot of ML platforms, rightly so, try to automate some of that, and to make not only the feature list, the date range, and the feature versions explicit, but I think what I found is even when those things are true, when for a given model you have this sort of let's say like a SHA of the feature version and a date range and a feature list, you still oftentimes have the problem that even though you have the artifacts, or rather the ledger of what that training run was, it is actually very hard to rerun the same model. And so there's actually a central failure point, which is if for some reason you even lose the binary file of your model, it should be sort of feasible to automatically retrain the same model on the same data with the same feature list. So that very quickly becomes very hard, right? Because maybe the features have changed and maybe you've deprecated some versions of them. And so that I think is still a challenge currently. Similarly, data sets change constantly, especially in industry. You realize that some of your features are wrong. You want to add some features. You want to improve upon some features. And I think that that's also an area where most ML platforms have made it so much easier to take an existing data set and process it further, or take an existing data set and join it with some other data that some other team is using and use it to enrich your own models. One area that I think is still really promising to explore and hasn't been explored much is sort of capturing new events to derive features from. All features eventually come either from some transactional data or from some logging that you do at some point in the pipeline. And that means that if you want to add a new feature, oftentimes you want to add a new logging system, verify that you're logging the right thing, wait for those logs to propagate all the way, generate a training set, and then train a model on it. But feature exploration by its nature is work where you don't know what the impact of a feature will be. And so I think making it easier to test with less investment whether a potential feature would be good is actually a really valuable part of the workflow as well. Finally, on data management, I think another sort of common pain point of data scientists and interesting directions I've seen platforms take is sharing representations. This is an example from Stitch Fix Style Shuffle, where one team at Stitch Fix has essentially a Tinder for clothes, where you say, oh, I like this top, I don't like this top. And that model creates embeddings that they then propagate for other teams to use, in basically any other ML application that they want. And that empowering that kind of application is super powerful and takes a data store that can store something that's maybe a little bit odd, right? Which is allowing the storage of arbitrary vectors keyed on arbitrary features so that they can be shared. I think this is something that has started to happen more and more, but that can really enable some cross-functional work. All in all, for data storage, I think it's interesting to think of data sets as sort of like a reproducible feature of a model, meaning fully reproducible, and so a model being fully trainable on this new feature, um, and having not only the raw data but any intermediary representations, including feature vectors, being shared with other teams. Maybe more interestingly, and more um, at the intersection of ML and platforms, I want to talk about performance validation. So again, you have models, and you train them, and usually you backtest them, and that's how you decide whether you're going to release a new model. Earlier today, Zipline talked about, for example, like preventing time traveling. I think one thing that's interesting here is, even though in regular software you can have sort of like thorough tests and be relatively confident that your application will work, that's not the case in ML. You can have all of your tests passing and somehow you ship your model and it's still bad. And one of the main reasons for that, again, is data leakage. If you use production data, it's almost impossible to prevent time traveling. And so a lot of sort of Lambda architectures like Zipline or like Semblance at Stripe address this by using event streams in order to recompute what the state of the world was at a given time. I think those abstractions are very powerful, but I wanted to use this time to just call out that they can never make data leakage disappear entirely. And I'll give you an example of sort of my favorite pet peeve, which is separating data randomly. What is commonly done for testing a model, right, is you take 30% of your data, you separate it randomly from the rest of your data, you train a model on 70%, and you test it on the held up 30%. It turns out that even if you're given a data set with no time traveling, but it has, for example, a date range, if you perform a random split, then the model you produce will have data leakage. If somehow your data contains duplicates, you'll have data leakage. And if you have somehow multiple measurements for sort of like a unique customer or a unique embedding, you'll also have data leakage, and that will lead to your offline measurement overestimating the performance of your model, and then that will lead to you deploying your model and being very sad. I call that out because even though it's great that we have tools to sort of reduce the burden of the practitioner and make it harder to make these kinds of mistakes, the real way that you can tell whether your model is working well is by deploying it. And the way to make that to make that evaluation easier, to make that process smoother. Here I've sketched out sort of the difficulty of, or the risk of the evaluation of a model compared to its accuracy. So the least accurate method is the held out test set that we just talked about, but it's also not risky at all. Slightly more risky, because you're increasing load on your production systems, is to run the model in shadow mode, where it's scoring, but you're actually just throwing its predictions away. You're not using it in your production app. But that is much more accurate, because then you'll see features as they come in, and you'll be able to actually accurately compute its performance. And finally, the most accurate is to run a model in production. Also, obviously, the most risky. You should not start with that step. But I think the interesting thing is some of the tools that have made the most meaningful changes to workflows are the ones that actually allow you to seamlessly go from one to the other, from one part of this graph to the other, right? So that you can simply promote a model shadow, see if it's doing well. If it's doing well, you feel relatively confident to run it in production. And if it's not doing well in production or in shadow, it's easy to take it back and it's easy to roll back. And that's actually in some ways much more helpful than trying to nail down the last 10% of sort of data leakage issues that could arise. So yeah, I guess the takeaway of this is, instead of trying to reduce data leakage entirely with sort of like preventing time traveling in feature store, or instead of eliminating it, try to reduce it instead. Model deployment is the bottom part of this graph. I think it's interesting for sort of two main reasons. One is, to many ML folks, before they've worked in industry for a bit, model deployment seems like the simplest problem in the world, right? You train a model, and then you save the binary, and then you load the binary. But as you know, and as I'm sure you've seen today, it's a little bit more complicated than that, right? There's different model versions. Which date was the model trained on? What version of the data matters? Did you filter out any particular user regions or any particular criteria that would make your model not apply well to these particular users? This is something that automation obviously helps with a lot. You can add sort of arbitrary, in this graph, I add like the pre-processing as something that is also hard to keep track of. And if you start deploying manually, or if you don't have a tool to help you keep track of that lineage, it's very common to just ship a model that's on the wrong feature version, on the wrong app version, or with the wrong pre-processing. I've done that before, and those errors are not only common, they're also really hard to debug. So tools that help with that have been extremely useful. Finally, I think there's something that I haven't seen tackled much, and that might have been because I haven't looked at the right areas, but almost every model I've ever trained and shipped has suffered from some version of staleness. If you're predicting click for ads, or if you're trying to predict demand for any product, or if you're trying to detect fraud, patterns in the world change, and so you need to retrain your model every n days, every n months, every n hours. Usually, this retraining, at least for a while, is done manually. Actually, usually it's just not done until somebody notices that the model is going completely stale, and then they retrain it. But this is something that could be fully automated, and in fact, knowing things like what is the optimal retraining period, how long should we wait until we retrain to balance the inherent risk of rolling out a model and the staleness of the current model, is something that would be really helpful to have as a first-class citizen of ML platforms. So again, 2 points. Helping with versioning and helping with automatic redeploys is something that is probably the most toilsome aspect of model deployment for humans currently, and that ML platforms can and should do well. Monitoring and alerting is maybe even more important here, and this is by design. I've gone from maybe the most benign to the most important aspects, in my opinion. So monitoring, comes with you ship a model. In theory, everything goes well. In practice, it doesn't, because that's just the rule of engineering and of machine learning engineering specifically. There's many reasons why a model could fail to perform in production. I've put 3 here that are common, or that have been common in my experience, which is somehow your input distribution changes, somehow some part of your model causes an increase in latency, or everything looks fine, but all of a sudden your output distribution seems to change, and that indicates that maybe something is wrong with the model itself. These bugs happen, I don't want to say they happen on every model release, but they happen frequently on some model releases. And as the person that's been tasked to debug them, I found that while automation helps with releasing models, it can be really hard to debug what's going wrong when all you're given is an alert of, the mean score output of your model used to be 0.4, and now it's 0.2. There's no significant difference in the statistical distribution of your input data. What is wrong? And what's been the most helpful for those is sort of regular inspection points, where you can look at your data when it's coming in raw. You can look at it after you've cleaned it. You can look at it after you've generated your features to try to see if somehow some part of your feature generation pipeline, due to for example, a production change has broken. And you can look at the features right before they're fed to the model, and at the predictions of the model right after they come out of the model, before any further filtering. Any system that's allowed me to do that has saved me hours. It is nigh impossible to debug model issues without having that sort of visibility. And it's not always easy to provide it by default. Just relying on tools like Splunk or other logging tools doesn't give you the sort of aggregate views that you sometimes want to see, right? Sometimes you just want to say hey, what is the proportion of time that this feature is null, or that this feature has this value? So things like TF data validation and others, other recent advancements have really helped with that aspect of things. I add this as a nice to have on top of observability. Alerts can be really helpful when it comes to helping ML folks debug models. One caveat of alerts is that if you have an alert on is the proportion of nulls on this feature higher than expected? Let's say that higher than 5%, and you have 400 features. It's hard to tune a threshold that will not give you a bunch of false positives. And so a lot of alerting systems suffer from that, where every day you have 55 feature alerts, and because you have 55 feature alerts, you just sort of learn to live with it, and you just ignore them entirely. And so what I found is tuning thresholds pretty aggressively at the cost of missing some alerts to make sure that you actually have time to action each alert that comes up. All right, and one of my favorite topics, and one that I haven't seen any ML platform handle currently, but would love for that to not be the case anymore, is error preemption. And so this is actually core to the application logic, and I think this is why ML platforms so far haven't tackled that aspect as much, because it's very hard to build a generalizable solution. So this is maybe more of a pipe dream than a feasible outcome, but I think it's something that actually causes a huge amount of pain for engineers and ML engineers, and could really reduce toil for many model deployments. And the idea here is that a model, a machine learning model, will produce predictions if it receives inputs. If the data is in the right shape, your model will make a prediction. At the bottom here, you can see an example. This is a model that classifies whether a question is about language or cooking. I imagine that being used by like Stack Overflow or something, or Stack Exchange, which has more general questions. And you have a sentence, the model transforms it into a vector, then it does essentially a bunch of matrix multiplications, a softmax, and it outputs a prediction. If you replace that sentence with absolute nonsense on the right, your model still makes a prediction. Maybe it's slightly less confident, but it's still going to make a prediction. And this is true for sort of like any ML model ever, right? As long as data is in the right side, it'll make predictions. But sometimes the data will be of the right size and will be absolutely wrong. And so how can we know if that is the case, and how can we sort of proactively prevent it, since we know this is something that will happen? One thing that ends up just happening in practice is that somebody at some point in application code writes some input check that checks for the presence of feature. It checks for like, are they within a statistical range that we've seen, in training, and potentially checks the model score itself to say like, hey, is the model like confident, or is it sort of like outputting a 50-50 in terms of its output probabilities? And based on that check, usually what you'll do is you'll run the model if everything looks good. If there's still enough information, but you don't have enough to run the model, sometimes you'll run a heuristic that can give you some of the value, but not all of it. And if it just seems like there's no way that a model or a heuristic would succeed, you display an error. If you think about it, there's no reason that should be written in application logic for every single ML application. This could be something where you just have a first class or like filtering block where you define these primitives, and they're just handled gracefully that way. To help with that, a lot of ML teams also have some sort of anomaly detection, right? Where they like say, hey, if this value is above this certain threshold, then it's probably an anomaly, and we can just outright, reject it if it's like, in this example, like a number of login attempts for a user, or just not even run our model. This is also something that is custom built every time, but doesn't necessarily need to be. And finally, one of the approaches that I find the most elegant, and that maybe is the most suited to ML platforms, is an approach that is used by many product teams. And one of the examples is it's explicitly called out in the Google Smart Reply paper, which is a paper that's about Google's method to propose replies for emails. If you've ever used it in Gmail, you receive an email and there's like a few replies that are suggested to you that are sort of like quick replies that might apply to this email. The model they use to generate those replies is actually costly and can fail on input that, like a complex email. And so they have a very simple logistic regression ahead of it that classifies the input as, is this the kind of input that a model will run well on? And so it maybe seems a little recursive where you have a model to tell you whether you should run your model. But running filtering models actually makes a lot of sense in many practical cases. It helps reduce costs overall because you can run the super simple model and then never pay the inference cost if the filtering model says you shouldn't. But you can also sort of just guard yourself against failures of one model by having two models make that decision for you. And that's something that also could be facilitated a little more, because usually it's just done by, again, hand wiring this like first model that you've trained and then the second model, and then you have to keep in mind the relationships between both. And when you release one, it implies releasing the other. And that seems something that very much could be automated and could add just a huge amount of lift. So the takeaway of this section is that models, will make errors, and usually application code is written to sort of catch those errors ahead of time and to make sure that the user experience is salvaged. But if this is something that you have to write for every single model that you'll deploy ever, then it probably makes sense to have the system that's in charge of helping you deploy models have a permitted for you to write it more easily. All right, we've covered a lot. As always, I probably had a few too many slides, but here's a takeaway slide that I hope clarifies any lingering questions you may have, which is, if ML platforms are tools to help manage inevitable model failures, then for each of the below aspects, these are likely, in my humble, again, user review, the things that offer the most lift, and that probably should be first-class citizen in any ML platform. I'm happy to share the slides later. I think they'll probably be on Data Council's website, so you can have a look at them. But in the meantime, that's all I have. I want to thank you all for attending. If you have more questions, or if you want just more sort of ideas about deploying ML or ML platforms, as Pete mentioned, I recently published a book. You can read its first chapter for free at that URL, or reach me on Twitter. Thanks.